Hey, Math 1 students, this is Mr. Dobner, and we are taking a look at the 1.6 Ready, Set, Go skills notes. So let's have a little bit of a review. For arithmetic sequences, if you have an arithmetic sequence, what you need to know is that for an arithmetic sequence, you're going to have a pattern that involves adding or subtracting. So we could real quickly just remind ourselves of that, an adding or subtracting pattern. And there's a very important word that we have as well, the common difference. The common difference is the amount that is added or subtracted. So we've been talking about that quite a bit, and we're going to take a look at a few problems right below. And the thing is, we will be told that we have an arithmetic sequence. So taking a look at number 1, it says find the missing terms for each arithmetic sequence. You can see we're underlining that right there. We also want to state the common difference. So we know that we're adding something to go from 3 to 7. And you can see over here we've got 15 and 19, but we've got some gaps. So hopefully you can see that we are adding a 4. And by the way, you could always, just use a calculator to subtract that second number minus the first to find it. That's why we could call it a common difference. But finding that there is a plus 4, you can confirm over here, going from 15 to 19, you would be adding a 4 as well. Well, 7 plus 4, you will get 11. Sure enough, checking that you're right, 11 plus 4 will get you 15, and then 19 plus 4 over here gives you 23. So you're going to have to fill in these missing gaps, but you also want to write this number that we are adding. The common difference is actually a 4. Now, in this kind of a sequence, you can see each of these terms, we were getting larger. We were going from 3 to 7 to 11. We're getting bigger. And that's because we're adding this positive number to each of the previous terms. When you look right here, going from 5 to 3, you can see we're actually getting smaller. And we very quickly can see 5 minus what would be a 3? Well, it would be a minus 2. And likewise, you can also think of subtracting 2 as adding a negative 2. So, right here, we're subtracting a 2 just as well. If you've had difficulty with signed numbers, feel free to use a calculator and, get a double check here. You could very quickly, get this thing turned on. It's a little having some difficulties here. Here we go. We could say 1 minus a 2, you could see that we would get a negative 1. And, it's easy to just continue to add this negative 2 or subtract a 2. Negative 1, and think about it in terms of money. You have a debt of $1. You owe somebody $1, and then you lose $2 more. You get $2 more in debt. You can see you're actually going to be at negative 3. And we could use our calculator to confirm that. You add a negative 2 or subtract a 2, negative 3 minus 2, you'd get negative 5. So our common difference will be negative 2. As we take a look right here at this next one, perhaps number 3 is the most different. It's all written out in function notation. We can say if f of 2 equals 7, if f of 3 equals 10, and these are terms in an arithmetic sequence. Well, look, at making a list, what you're really saying is this. Your second term, your input, would be a 7. Your third term would be a 10. That's really what this f of 2 equals 7 and f of 3 equals 10 is really saying. And now you can look and say, well, it's arithmetic, so what exactly am I adding? Well, you could say, looks like I'm adding a 3. So what would the fourth term be? Well, you can add a 3 real quickly and see you'd get 13. For your fifth term, you add a 3, you'd be up to 16. So f of 4 would be 13, f of 5 would be 16. Here's another way you could look at this. Let's just say that we made a table off to this right-hand side, and we have n and f of n. You could say f of 2 equals 7. That's like 2 and 7. Your input is going to be your n, and your output is going to be a 7. So you could say 2 comma 7, then you could say 3 comma 10, and then you pretty much see the same thing. You could say, well, I'm adding a 3. I'd add a 3 right here. We'd be at 13. Coming down this way, we'd add a 3 again. So it's a different way of looking at that. But for the recursive function, hopefully you remember it's the now equals the previous. We could say f of n will equal f of n minus 1. But what are we doing each and every time here in this arithmetic sequence? Well, you can see we're adding a 3 to the previous term. And that's really what we're doing right here. So you can say plus 3. So that is not sufficient, however. You need a beginning value. And this f of 2 equals 7 is necessary to write down for the recursive function. All right, as we go to the geometric sequence summary. For a geometric sequence, really what we're going to see is that we've got a multiplying pattern. With this multiplying pattern, sometimes kids will say, could you think of this as dividing 2 if you're getting smaller? Well, I suppose you could. However, please be careful. The common ratio very, very specifically is going to be the amount that you are multiplied. The amount that you multiply to each previous term. So if you're getting smaller, sometimes kids might think, oh, I'm dividing by 2. Dividing by 2 is the same thing as multiplying by the reciprocal, multiplying by 1/2. So we have to be careful about that. Take a look here at number 4. It's incredibly close to number 3. It says 2 consecutive terms in a geometric sequence are given. And take a look at this. F of 2 equals 5. Well, you can make a list. You can say, okay, so my second term here is a 5. My third term, f of 3, is a 15. And then could we find our fourth term, and could we find our fifth term? Really, that's just writing these extra things down here underneath, showing the term number, the input, so to speak. And, as you're going, knowing that you are multiplying, going from 5 to 15, we're multiplying by 3. If we were to continue to do that, 15 times 3, you could quickly confirm would be 45. And then if you were to multiply 45 by 3, again, you could confirm this on a calculator. You'd get 135. So what's f of 4? Well, f of 4 would be 45. F of 5 would be 135. And again, please understand, you are more than welcome to make yourself a table if you would rather. And you've got this right here. You could say my input is a 2, and my output's a 5. That's what f of 2 equals 5 is really saying. f of 3 equals 15. That's right there. You can see that you're multiplying by 3. You get the same thing. 15 times 3 is 45. And 45 times 3 is going to get you 135. So either way, you're good to go. For the recursive function, though, we're going to write f of n equals f of n minus 1. That's your previous term. But what are we doing to each previous term? Well, we've seen it. We've seen it as we made a list going from term to term to term. We see it if we made a table. You can see pretty quickly that's a multiplication of the previous term by 3. So your common ratio is going to be a 3. You also have to have a beginning value stated. So f of 2 is equal to 5. So just wrapping this up, here you can see for number 5, we have an explicit function. We have f of n is equal to 3 to the n. And very quickly, remember that what we have here is our input. That's a 5. So whatever we put in for n right here, we put up as this power. This will be 3 to the 5th. And 3 to the 5th is literally 5 3s multiplied together. And could we do that quickly? I hope so. Here's how. You could go 3. Right above the division button is this caret button, the power button, and we'll get 3 to the 5th is actually 243. Look, we can do the same thing with this problem, plugging in a 0. That's 3 to the 0. And I hope you know what 3 to the 0 is. If you ever wanted to double check, you could do that right now. 3 raised to the 0 power is actually a 1. So it's good to be able to check things on the calculator. Taking a look here at our very last one, again, an explicit function. Our previous one dealt with exponents. That was geometric. That's some nice review right there because we have that n raised up as an exponent. For number 6, we don't have our explicit function dealing with exponents. We've seen this pattern quite often. This would refer to an explicit arithmetic kind of a function. So if we were to plug in a value for n here, we'll have to plug in a value for n right there. So look, plugging in a 4, you'll plug in a 4 where you see that n as well. Now, again, I'd just suggest that you use your calculator as a way of double checking. You don't want to make a silly mistake on one of your assessments. So without too much work, you can see we're going to get 11. You always have to do what's in parentheses first. 4 minus 1 is a 3. But then you'd have to multiply that value of 3 to the 3 to get a 9, and 9 plus 2 is 11. That's the order of operations. We can circle these answers right here. One last one. What about substituting in a 1, f of 1? So replace n with 1. Here you'd get 2 plus 3 times 1 minus 1. And of course, you know that 1 minus 1 is a 0. I think that can help out. And 3 times 0 is 0. Hopefully you have a pretty good idea what you're going to be getting here. It's effectively 2 plus 0, isn't it? Which is just a 2. All right, good luck.